My name is Sameer Shende. I'm here from the Performance Research Laboratory at the University of Oregon, the home to our Tau project. The Tau performance system is a parallel performance evaluation framework that supports all HPC platforms, compilers, and runtimes. Our goal is to support all of these systems, and it provides portable instrumentation, measurement, and analysis capabilities. If you look at the architecture of Tau, there are many ways to add hooks to your program in Tau. Whether you're using C++, C, Fortran, and whether you're using MPI, OpenMP, just a show of hands, how many people here use Fortran? And C++? C? Okay, that pretty much covers the audience. We can insert hooks in a variety of different ways, going right from the source code to the linker and even at the binary level. And once these hooks are in there, you can measure the performance of your code using profiling as well as tracing. And we heard earlier today about the differences between the profile and the trace output. Tau also supports sampling. So you can have sampling as well as direct instrumentation hooks in your code to precisely measure the performance. And then once you generate the performance data, you can use our ParaProf and PerfDMF database and Perf Explorer tools. Or you can use Vampire, JumpShot, Paravere, and other tools for trace analysis. So there are these three parts: instrumentation, measurement, and analysis. And we have support for a variety of different threads and runtime systems. What we'll see here today is MPI with OpenMP. We will use ScoreP for native trace generation, and ScoreP provides a very efficient generation of call paths. And it's we have noticed that ScoreP can produce very precise, compact information, and it works better than the legacy measurement library that Tau provides, especially for efficient call path generation. So that you should definitely check out. And then we have ParaProf and Perf Explorer tools that we'll show. So to recap, Tau supports both sampling and direct measurement. It supports other features as well, such as memory debugging, I/O performance evaluation, profiling as well as tracing, and interfaces with ScoreP for more efficient measurements. And there are a number of other things that we'll describe in this talk, including runtime library interposition using a tool called Tau exec, the compiler-based instrumentation and source-level instrumentation, even sampling, and so on. And we'll look at the Tau exec tool a little more in detail. But probably you're wondering, what is it that Tau can tell me about my code? What kind of questions can we answer with Tau? The first question is, how much time is spent in my application? In which code regions? At the routine and the outer level loops. And within the loops, what is the contribution of individual statements? What is the time spent in OpenMP loops? How many instructions are executed in these regions, such as hardware performance counters that can show you detailed inner workings of your CPU? You may have questions about the memory usage of your code. Just how much memory does my code use? When and where is memory allocated and deallocated in my code? Are there any memory leaks? What is the memory footprint? The total amount of RAM that the application is consuming. What was the maximum memory that my application consumed at any point during its execution? You might have questions about the energy usage. How much energy does the application use in joules? What is the peak power usage? Or what's the I/O characteristics of my code? Peak read and write bandwidth for POSIX I/O. What is the total volume? You can even look at the performance of your code within phases. So you could see what is the time spent waiting for resources in a given phase of your program. And how does the application scale? What is the efficiency, runtime breakdown of the code? So when you want to use Tau's source code instrumentation, there's a couple of things to remember. The first thing is, when you install Tau, you tell it which compilers to use, which runtime to use. Whether you want to use MPI with OpenMP or MPI with pthread, or if you want to use a specific package such as PAPI. And whenever you configure Tau, you create a unique stub makefile or a configuration file whose name is created with tags. To instrument the program automatically using our static analysis tool called Program Database Toolkit, we just have to first set up the Tau in our path, which can be done with this source command. And then you set this Tau makefile, which points to the configuration file. And the name here suggests what it can do, such as it can track MPI data, it can do source-to-source instrumentation by parsing the code, adding hooks to a copy of your source code, and creating the object file. And then you can change the name of your compiler from tauf90.sh, from MPI-FRT-PX to tauf90.sh. You can compile the code, you run it, then you can use pprof or paraprof for the GUI and analyze the data. Here, you do not need to change anything in the source code, mind you. You just set some environment variables and change the name of the compiler. Okay, you can compile the code this way. If you source this setup.sh, you can see that this $tau gets defined. And if you see which configurations are available by doing an ls makefile.star, you will see that there are makefiles or configuration files for using MPI with source instrumentation for the Fujitsu compiler, or using, instead of the legacy MPI library that Tau provides, you can use ScoreP for the measurements using this configuration. If you want to do instrumentation at the OpenMP level, you can use the Opari tool, also from Research Center Jülich, by choosing this configuration, which uses the Tau's native measurement library, or use this, which uses the ScoreP library. So if I had like an MPI with OpenMP and Fortran 90 application, I could, for instance, choose this for native Tau measurement library or ScoreP library. Just set this Tau makefile, then compile the code, and then you can run it and generate the profile files. Now there are many options that you can specify, knobs that you can tweak to change the behavior of the compilation process. For example, if I wanted to use compiler-based instrumentation, I could say set the Tau options environment variable to include an opt-comp-inst. Or if I wanted to track I/O, I could say opt-track I/O, or do memory debugging, and so on. You can also specify a selective instrumentation file which includes regions that you want to instrument or not instrument. So exclude or include list for functions and files can be specified here. Here are some other options for parsing the code using a separate parser. We recently added support for the gfortran 4.8 parser. You can specify a different parser like this. And when you're running the code, you can also specify some runtime environment variables. such as turn on sampling with tau sampling equals 1, or call path profiling or tracing, or tracking memory footprint of the program. You can also set the tau profile format environment variable to a merged so that you create a single file and not one file per thread of execution. If you are using PAPI, you can set the tau metrics environment variable to specify what is measured in a given performance experiment. Here are some memory-related environment variables. But we have tried to simplify tau's usage, and one of the key tools in that is a tool called tau exec. So wouldn't it be nice if I had my binary and I could just launch it with a different tool and not change anything? And I mean not change the source code, not change the make file, not change anything in the compilation process. If an uninstrumented binary could just be launched to generate all the profile data that you wanted. So we have taken steps to doing that with the tau exec tool. And if you just launch it with tau exec, it shows you the MPI performance. So you can see what was the time spent in my application versus the time spent in all the MPI calls. You can enable a number of other flags such as memory debugging or event-based sampling. Event-based sampling is a very powerful technique. You can take samples. We heard earlier in Brian's talk that you can use samples along with direct measurement. So samples can show you where the program spent most of its time. It's not as accurate as direct measurement, but it's a low overhead technique that can pinpoint regions of interest. Okay, you must take this with a pinch of salt because you are told that we collected so many samples at this line and this function is important, and so you can focus your attention on that. But it provides a very useful way to creating a sample-based profile by just saying tau exec-EBS. We can also use tau exec to look at the performance of GPU operations, such as looking at the CUPTI interface, the OpenCL library interface, and even OpenACC. In this audience, are you interested in accelerators like with GPUs? A few people? Okay. So you could use that without changing your application at all. We also have tools for Intel platforms and a couple of other systems where we can use a binary rewriter, where you read the binary and rewrite it with all the instrumentation hooks. This technology is evolving and we expect it to mature steadily. So these are the three different stages: instrumentation or adding hooks, measurement, or creating profiles and traces, and then analysis using ParaProf, the TauDB database, Perf Explorer tools. We can even save these files to a Tau portal, a web page where you can collaborate and look at the data. And when you create traces, you can use a variety of different tools, such as Paraware, like we are going to see in this workshop. You can create profiles and traces. If you choose to create trace files, you can turn on tau trace equals 1, generate trace files. You can use tau tree merge.pl and create a merged trace. And then you can say tau convert these traces into the Paraware format. and then launch WX Paraware, and you will be able to see the profile, the traces in Paraware, or Vampire using ScoreP. So this is the architecture of ParaProf. We support a number of different profiling tools. We can connect to the databases and show you a variety of different call tree displays, 3D displays, bar charts, call graphs, histograms, and so on. This is the 3D display from ParaProf. On one axis, you will see all the threads or MPI ranks. On this axis, you will see all the function names, and the height can be the exclusive time, and the color can be chosen as well. And we have this slider which can go from this function to there, and then the thread from here to there, and where it intersects, you can see the total height value and the color value in this 3D profile browser. You can click on it and rotate this 3D display, and I'll show you how to do that. And you can click the right mouse button and translate it, so you can move it. And yes, you can use this on the Fujitsu FX10 system with a remote display with the 3D graphics. And it's sometimes very useful because you can see here I have 2048 ranks, and I can see the shape of the profile. I can see that MPI send slopes down with respect to the ranks. Although I don't have 2048 pixels over here, I can still see the shape. And so this scales very well to really large core counts. Here is the communication matrix display. I showed you some runtime environment variables. One of them is tau com matrix equals 1. If you turn this on, you will be able to see what is the extent of communication between senders and receivers. So where they intersect, you can see the height, which can be the message volume in bytes or number of calls and so on. So you can see the shape of communication. We have both 2D as well as 3D communication displays. With PAPI, tau can generate a variety of metrics. These can be metrics such as floating point instructions used in a processor, or in this case, for the Intel Xeon Phi, I'm looking at the number of VPU vector processing unit elements that are active and looking at the instructions executed. There are 512-bit wide instructions on the Xeon Phi, and you can fit 8 double precision or 16 single precision elements in each instruction. So you can see by dividing the number of active elements to the instructions executed and sorting it by the time taken, you will see the list of functions sorted by the functions that you care about the most. And for those loops and functions, you can see how close am I to 8, which is the max you could reach for double precision, and so on. You can also compare different runs in tau. Here is an example of an optimization that we are working on. The original profile file shows that the time taken was 528 hours. Then we tweaked it, we changed the communication pattern, and the time fell down to 271 hours. And then we use a different FFT optimized library provided by the vendor, and the time drops down further to like 70 hours, from 528 to 70 hours. And you can compare what happens to each of those functions by looking at the profile. You can also see the histogram view in ParaProf. Here, I can see within buckets how many threads belonged in a given bucket. If MPI all-to-all V executed anywhere from 1.5 seconds to 2.5 seconds, and you hover your mouse over here, you can see that the number of threads that took between 2.1 and 2.2 seconds was about 295,000. That's the number of threads in that 2.1 to 2.2 interval. You can change the number of bins by going to the options. Here is an example of energy profiling tau, where we can see the power used in watts for the package 0. This is from PAPI. And this is the ParaProf manager window, where we can see with all these green balls here, we can see metrics, different metrics. In this case, we are looking at a cubex file generated from Scalaska. We'll look at Scalaska later, but here is, in plain English, a bottleneck that it has discovered, such as the time spent in a late sender performance property where messages were sent in the wrong order from different sources. And you can click on that metric and see how all the different threads were in that case. You'll see nodes and threads like this. And you can look at the thread statistics table, where you can click on a given column or move the columns around. So you can click to sort a given metric, drag and move and rearrange the columns, and you can open this key to see the components within that particular node. So this is the parent, this is the child. And if you set the call path depth to, say, a big value like 100, you could get a complete call tree. So you could see the time spent in this application, and then it calls SSOR, which calls RHS, and then BUTS, and then you open up this, it's exchange 1, and so on. And you can see the time spent in MPI receive along a given calling path. Okay? So a flat profile doesn't show you the structure like this. A flat profile shows you the total time in all the functions. A call path profile, on the other hand, can show you precisely what was the contribution of a function along a calling path like this. And you can expand and contract the nodes in this tree. Here is another view of the call path thread relations window, where an arrow indicates a given function, and anything above that arrow is its immediate parent, and anything below that arrow is, in that block, its immediate children. So you could see that the function parallel, OMP parallel RHS, took 2.5 seconds, and it only came from one function called compute RHS. But this 2.5 seconds of inclusive time had contributions from all of these other OpenMP regions that it called internally. So what is the objective of our demo today? We want to familiarize you with the usage of Tau's tools and help you apply these tools to your applications. And we have an exercise that's based on this NAS parallel benchmark, but it will just help you understand how to use the tools and be productive with it. Okay? And then there are some other extensions. We'll look at the performance of other configurations and investigate system-specific compiler features or MPI optimizations, and even compare performance on different HPC applications, platforms, if you would like. So the same tool is used in the same way on different HPC platforms. If you learn how to use Tau on the Pi system, you could apply the same techniques on a Linux cluster with x86 64 systems. So we have installed Tau. What I would suggest is each one of you, for this hands-on session, please include this statement in your .bashrc file, the setup.sh. That way, all the tools that you launch will be in your path. That way, if you launch a tool from a job submission script, it will find the location of the tau exec tool. So put this setup.sh in your .bashrc file. And when you generate a profile file from Scorpy, you can launch the cube as well as the ParaProf profile browser to view its contents. Here are some examples for Perf Explorer. We'll go into that later. So by now you're familiar with the NAS parallel benchmark. I will not describe what it does. Here is a config make.def file where you can see how the default compiler is chosen as MPI FRTPX. And when you say make, it will show you this output. You can also say make suite, and it will build the B8 processor benchmark in the bin directory. And you can copy the run.sh script from the job script fx10 folder and just run it by saying pj submit run.job. It will create a file with a .o and job ID, which contains the output from the file, and you can look at how much time was spent in it, about 16 to 20 seconds. And you can then save this output and compare it with an instrumented run. Okay, so this is the MPI NAS parallel benchmark with MZ for BT. And this is the tool that I was describing, tau exec. These are some of the options that it can take, whether you're measuring I/O or memory, or in our case, enable event-based sampling. You can change the interval period when the samples are taken. You can change hardware performance counters that are used for sampling and specify different tau tags using the -t option. So you can pick up a configuration of tau that you wish to measure against. You can even run the GDB debugger with that tau exec tool. The default is an MPI configuration. So what you can do really is just launch tau exec-ebs and run the same program. Okay, let's try this. Put this in your .bashrc file, do a make clean, make suite, build this binary, and edit this run.sh script and add the tau exec-ebs just where the executable was. So there is no change to your binary in any way. It will just generate profile files when you run the program, and then you can launch it with ParaProf. Okay? You should see a thread statistics table like this when you right-click on a node and say, show the thread statistics table, and then you can click on a column to sort it. The commands for doing this are all there in this readme.tau file that I just before the talk requested that you copy in your area. Okay? Let's just look at this readme.tau so you can look at the instrumentation, and let us try building this code. So